Okay, greetings and salutations. Welcome to the afternoon portion of the Gluster Community Workshop. Dustin Black is going to speak in a minute, but before we do, I just wanted to post the URL to this go to the survey, for the survey for this workshop. So please give us your feedback about this survey at that URL, and we'll use that to make a better workshop in the future. So it'd be great to have your feedback there. Next on the lineup is Dustin Black, and he's going to give the all about SysAdmins, or GlusterFS for SysAdmins. And then I'm going to connect his computer. Can somebody shut that back door, please? Where's this? Oh, we have one of these fancy ones. Cool.
All right, testing. Everybody hear me? It's going over the speaker. Okay, thanks for everybody for joining us this afternoon after lunch. Hopefully you're not too calorie-ridden to start snoozing off while I'm talking here. I'll try to keep the pace up. My name is Dustin Black. I'm a Red Hat certified architect and a technical account manager for Red Hat. I'm a systems guy. I'm not a coder. I want to make that evident right up front, so there's a lot of the deep down questions I'm not going to have the best answers to, but luckily we've got some great resources here if your questions go beyond what my expertise may be. Just a quick little bit about what I do for Red Hat. I work for Red Hat Support. I am a semi-dedicated resource for a set of customers. A lot of my customers are in financial services industries and pharmaceuticals. I tend to them as personally as possible, get to know their environment, and try to provide a high level of service for them in as personable way as possible. We manage a lot of the things such as multi-vendor support issues, and we act, one of the biggest things that our customers really like to take advantage of is acting as a customer advocate to Red Hat. I've actually got some customers who use the TAM service specifically for that because they want to have that high-touch access to engineering as much as possible. So what we're going to do this afternoon is take a look at GlusterFS from the sysadmin perspective. What I hope for everyone to get out of this, give me a second here. I hope you're going to see a lot of repetition in the beginning here of some of the information that's been discussed, but I hope by the end of this you get a little bit more of a tangible outcomes so that you can walk away from this and this evening, if you want to go sit in your hotel room and be a geek, you could spin up some VMs and install a Gluster system and start feeling like you're actually into the community and confident to use the system. So we'll start right off with the technology overview. So what is GlusterFS? We've talked a little about this. We've got a POSIX compliant file system. There's no central metadata server, which is going to get rid of a lot of those bottlenecks and problems that you have with those central metadata servers, as AB and John Mark had talked about earlier. We treat this as a network-attached storage system, so you're going to be able to access this over standard network protocols via a couple of different client methods. One of the big benefits here is being able to scale out the system with heterogeneous commodity hardware. So this is really sort of the building block for Gluster. It's how am I going to take all of this storage that's already there in a simple format and be able to expand out and use it as simply as possible without a lot of administrative overhead. And that's what we get into with you'll see in the administration of this how simple this scaling out really is. So we're able to take all of that hardware, all of the resources from those systems, and essentially aggregate them. So in the end, all of that storage, all of that processing power and memory is essentially pooled into one storage system. Let's see if the clicker works. So what is Red Hat storage? I'm just going to touch on this a little bit so that you have an understanding of what we're trying to do with the GlusterFS system and turn it into a supportable piece of software. So what we've done with Red Hat storage is we've taken the code of GlusterFS, similar to what we do with all of the upstream products, Fedora going to RHEL. We've taken that code, we've taken the pieces of it that we feel are most prepared for an enterprise environment, and we've tested those and certified them with hardware configurations and with our partner vendors, and created something that we believe is a supportable environment for GlusterFS. We package that and distribute that as Red Hat storage. Uses an entitlement process very similar to how we do Red Hat Enterprise Linux, and you end up getting the world-class support that Red Hat's able to offer with the Linux environments, also with the storage. What you also get, and this is one of those trade-offs when you're going from a community environment to a enterprise environment, is you want the support. We're going to end up kind of limiting the way you use it. That's just a natural thing here. So when we build this, it is GlusterFS running on a RHEL system plus XFS. Now we include XFS, which is generally in RHEL 6 as an add-on entitlement, but it's part of the Red Hat storage system. We use a subscription model just like we do with all of our entitlements for Red Hat Enterprise Linux. And we have a couple of different flavors of this. The main one that you're going to see is the storage software appliance, which is for deployment in the data center. And there's also the virtual storage appliance, which is for public cloud deployments. So comparing GlusterFS to your traditional storage solutions, where does this really going to fit in? Where am I going to use this? If you look at your basic NAS solutions, your NFS servers, you're going to be limited in scalability and redundancy in general. Your other systems that they've talked about that do allow you for scaling out are typically going to be relying on a metadata server or a metadata distributed set of servers. And in either of those environments, you're going to be limited to total scale and capacity. You're never going to get linear scaling. Then you can go all the way to SAN. And of course, SAN is great, right? SAN is expandable, it's fast, but it's also expensive, and you got to pay costly SAN administrators and network engineers to handle the thing. And it's not simple to deploy, and it's not inexpensive to deploy. So Gluster kind of fits in where that hole is. It's like we need something that's NAS performance and NAS simplicity, but we need to be able to scale like we can in a SAN environment. So what we're able to do with Gluster, with that commodity hardware, is get it into a linear scaling fashion and do this with little overhead, high redundancy, and make it as simple and inexpensive to deploy as possible. The clicker is going to work. The technology stack. So we'll just take a look here at how this is built up. Quick little bit of terminology. Some of these things you've probably heard passed around, but we want to put in some definitions here real quick so that everybody has a good understanding here. A brick is what we're going to refer to as a file system mount point that Gluster is going to use as a place to store its data. So that term gets tossed around a lot with Gluster, but it's really that simple. It's just a file system that we've told Gluster to use. A translator is a piece of logic. It's what sits between that storage and what's being presented in the global namespace to the user. So the brick being the storage component, John Mark had used the analogy of Lego bricks, right? So when you get to these Lego building blocks from the storage component, I can snap them all together and I can scale up the amount of storage capacity that I need. The translator gives me the similar capability with logic. It allows me to say, okay, I want to do different things with that data, and I can stack up the pieces of logic that I want to do and create the functionality. And you'll see that in the examples that I give here in a little while. A volume is essentially bricks that have been passed through translators. We have the backend storage, we have all the logic that sits on top of it. So the thing that gets presented to the user at the end is the volume. And then a node is simply just a Gluster server that actually is sharing those bricks. So foundation components, building this thing from the bottom up. What do you need to start with? Well, in your private cloud environment, in your data center, you're just looking at commodity hardware. These are x86 64 servers. And if it's a Red Hat storage server, it does have to be on the Red Hat hardware compatibility list. Now that's for Red Hat storage right now in the current release, that's going to be a limited set of servers and storage components that need to be used. If you're going to be using the community version, you're going to be able to deploy this on essentially any x86 64 hardware. In the cloud, what's realistic right now and what's available is deploying to Amazon Web Services. Obviously, as that landscape changes, you think we'll see some other options, but that's what we have at the moment for deploying to the public cloud. So we have this piece of hardware. Let's build the components up on top of that. So we need some underlying storage. This can be just some direct attached storage, JBOD disks. This is just storage like you know it. I'm going to attach simple storage to a server and make it available. Now on top of that, we do want to do hardware RAID. Now a lot of people wonder, why do I need to do RAID if I'm going to have the redundancy pieces that are built into Gluster? Why do I also need hardware RAID? Well, you really want to be able to handle a failure at the simplest point possible, right? If you have a disk failure, do you really want to be managing a disk failure at the Gluster system or at the operating system? You probably don't. The easiest way to handle a disk failure is going to be with your RAID environment. So it's highly recommended, and for Red Hat storage, it is required to have a RAID environment. Red Hat storage requires RAID 6. Logical volume management, also not a piece that's technically required. You can deploy a brick without LVM, but highly, highly recommended, and again required for Red Hat storage. And then on top of logical volume, obviously you're going to deploy a file system of some kind. This is going to be some file system that has extended attribute support. That's really the primary requirement there, because we're going to be storing metadata information in those extended attributes. So you're looking at XFS, ext3 or 4, ButterFS I throw up there as an example. It is possible. But keep in mind also, again, for Red Hat storage, the requirement is this is XFS. Now I see why he wasn't using the clicker. Okay, data access. So I've got this data on the server. What are my options for getting to this data? And we've talked about some of these options, and these options are growing over time as well. But this is what the main resources that you're going to see on the client side for getting to this. The Gluster native client, which is the file system and user space client, is typically going to be the best choice for most workloads. There are going to be cases where the NFS is going to be preferred, or one of these other methods, depending on what your architecture requires. So the file system and user space is the capability of doing file system functions, obviously in user space, not having to cross over into the kernel environment. This is built into Gluster. It's the native piece of it. It's what is most of the time going to be the preferred access method. We also have built-in NFS. This is NFS v3, as was mentioned earlier. This is built into Gluster, so the Gluster services are actually going to be running an NFS v3 server by default. Now, if you want to do Samba, this is a little bit different of a deployment. It's not built into Gluster the way NFS is. So for CIFS, you're actually going to use the Gluster native client to mount the share locally on the system and then re-export that local mount with Samba. So you're going to have a separately configured Samba environment to share those back out. And then there's UFO, which you've also discussed, and I believe Echo is going to get into some more detail on later. I'm not going to go too deep into this, but what we have the ability there to do is through some proxy logic that's in place is to access your data simultaneously, both as a file and as an object, which is a really nice benefit of Gluster to have that capability. So the pieces of Gluster that are coming out. Can you guys hear me okay? Seem to have lost the microphone. They run out of batteries. Okay, I guess I'm going to have to stand in front of this. Everybody hear me okay? Excuse me a second. So if you take a look at a Gluster node, what you're going to see as far as the services that are running are these primary ones here. So you have the Gluster D service, which is the Elastic Volume Management daemon. This is the main service that handles the Gluster communications. You're going to see this running once on every node, on every export server. You're going to interface with this through the Gluster command line tool, which is what we're going to actually show some examples of here in a little while. The GlusterFS daemon, this is going to be running once for each brick. So you may actually share multiple bricks from a node, in which case you're going to see multiple instances of the GlusterFS daemon running. This process is also managed by the Gluster D process. Then you have the GlusterFS process. This is going to serve a couple of functions on the system. One of those primary functions is as the NFS server. You'll see it running on the server side. You're also going to see this running on the client side, handling the Fuse communications. And then as far as the user tools that you're going to interact with, the Mount GlusterFS tool is the Fuse native mount tool. And then there's the Gluster command, which is going to be your management interface for actually working with the Gluster daemon. So I like this graphic. It shows you how all of these pieces go together. If you walk through the stack there, you'll see we've built this up from the bottom. We have storage. Give me a moment here. So we have our storage on the bottom, which then has the hardware RAID layer on top of that with logical volume management. And then, sorry, I can't see my own graphic very well. You can see how all of those components that we talked about stack on top of each other to, in the end, provide you the services that you're getting from the Gluster. I'll have all these published out. You'll be able to take a look at these in more detail, but I like this graphic for understanding how all of those components are stacked together. So scaling the system. This is the most important thing of Gluster, really, is its ability to scale. It's also so simple that I have two slides here just to kind of give you the basic concept of what's going on here. So our linear scaling up is our, this is, so looking at a single node, scaling up, adding disks to a node. So this is as simple as walking through those components that we discussed. So I have a server, I add disk to it, I add LVM, I put a file system on that, I tell Gluster that file system is a brick, and now I have additional storage. I can do this over and over again on a server. I can always add additional storage to a server. That new storage can become a brick, and we're able to scale up on individual systems. But the real power is also going to be in scaling out. We're going to take that process that we did, building up the system, and now we're going to just replicate that process over and over. With Gluster's ability to scale, you just do this again and again and again, and you're always going to get the linear scaling capacity because you're not having to deal with that central metadata server. And we also talked about this being able to be a heterogeneous process. So if you want that to be a larger server that you deploy, that's possible. That's something you can do. You can also take away a server. So we have this flexibility without being able, or without having to interrupt the end user to do this kind of scaling. Now, there's nothing limiting the way you do the scaling, but there are certainly use cases that are going to define how you might want to choose your heterogeneous environment. As you're growing a cluster over time, you may be adding newer, more modern, larger hardware, and that's most likely going to be your use case for things not being homogeneous. So what's it look like under the hood? The elastic hash algorithm is the core piece of logic that has Gluster doing what it does best, distributing the information between the nodes. So again, no central metadata server, so no bottleneck there. What we do is we hash the location of a file based on its path and file name, essentially. So what I like to compare this to, for anybody who's not familiar with this, is running an MD5 sum on a file on a server. So if I have a file, I run an MD5 sum on it, I'm going to get some value of a specified length. If I take that same file and I run an MD5 sum on another server, I'm also going to get the exact same value. It allows me to validate that that's the same file. you can imagine Gluster doing the same thing every time a file is accessed in the system. It is calculating a hash, and it's using that hash to understand where in the distributed namespace that file is located. And because every server is going to calculate the same hash, every server always knows the location of the file. It's able to use that. This is the primary thing that's keeping us from having to use that central metadata server. So the elastic part of this is we're not hard coding that hash to a specific storage location. We're coding that that hash value to a logical volume or a virtual volume. And that volume can then be assigned to multiple physical locations, multiple bricks. And this is what gives us our flexibility and elasticity. So taking a look at translators, this is just to kind of show you that pluggable and stackable capability that we see with the logic of the translators. There's going to be a stack of translators always on the server side and on the client side, and every transaction is going to be running through that stack of translators. This is just a simple example here that shows a fairly default scenario where the logic is passing through the client side and the server side and the communication. And you can see sort of a typical stack of translators for this. If you were to get into a more complicated scenario, you might see this branching off so that there's replication involved, or some of the pieces that, I'm trying to remember the specific example. There was a good example I recall of one of the translators that's commonly run on the client side that if you can also run on the server side for a different bit of functionality. So you can think of these things as modular, and you can get pretty creative in how you put them together, and also in developing your own translators, which obviously we would highly encourage. So we'll get into the meat of this and look at the basics of what we can do with Gluster. And a distributed volume is the starting point. This is what Gluster does by default if you don't tell it to do anything else. So a distributed volume is Gluster spreading the files essentially evenly across the bricks that are available. You can sort of think of this as file level RAID 0. Now granted, evenly is going to be a relative term because it's all going to depend on what kind of files you're writing, different sizes of files, different types of files. But it's going to do its best by default to spread these across. So you can see in this example here, when a file is written, you see file 1 getting written to server 1, and this example shows file 2 to server 1, export 1, and file 3 is going to the other brick. Keep in mind that we're looking at things at the brick level. In this case, we have one server with one brick, but this can get a lot more complicated. But we want to understand that the pieces that make up the distributed volume are the bricks themselves. So look at another basic scenario. Instead of distributing, we're actually going to tell Gluster, replicate. We're going to give it a command that says, okay, when you build this volume, you've got these two bricks, but now instead of distributing among these bricks, copy it to both places. Again, you can think of this roughly as file level RAID 1, and you can see that every file that gets written is getting written to both bricks in this case. It's just a simple case of a two replica scenario. So if you put these two ideas together, what I can do in this case is I now have 4 bricks involved, and I've told Gluster to make 2 replicas. Well, what Gluster's going to do by default, without me telling it to do anything else, is it says, okay, you've given me 4 bricks, you've told me to make 2 replicas, so now I'm going to distribute between the 2 replicas. So I've now layered these functions together, and I have a replication of each file that's being written between 2 bricks, and when the next file is written, it's going to be written to the other set of replicated bricks. So let's look at a little bit different scenario, the geo-replication. So what we were doing there was replication within a Gluster environment. We had multiple bricks on multiple servers and we're replicating our data inside of our data center. Geo-replication gives us the ability to handle remote replication for disaster recovery. So instead of it being a synchronous replication like it is within your data center, we're doing an asynchronous replication across a network environment. Now, right now, this is a master-slave model. As of 3.3, it's still only master-slave, right? Okay. So this is essentially a one direction replication. You can get a little bit fancy with this by replicating out in a cascading model like shown in the bottom graphic there. Once this is set up, though, this is a continuous and incremental process. In the background, this is essentially using rsync to keep the data synchronized between the remote environments. One important thing that I pointed out there is that time should be synchronized on all of the master nodes, otherwise this could get really out of hand and messy. But that's the basics of this is that we're taking our data and asynchronously pushing it out to a remote site. If you need to recover that data, you're going to be going through a manual process as it is right now. You do have it nice and clean sitting on your remote site, but there is no way currently with Gluster to replicate that back. There's no two-way replication yet. That is something that's being planned. So this is just comparing what you're looking at for the two different types of replication. You've got in-data center replication and multi-data center across the network replication here. Replicated volume is mirroring your data across clusters, and georeplication is for geographic distribution. So we did distribution and replication, and you saw how these are layered functionalities, but we're going to get into some more of those layers that you're capable of using with the basics of GlusterFS. So one of the other options we have, this has a relatively limited use case, but just so you can see how all of this stacks up, we'll talk a little bit about striped volumes. So you can think of this as similar to RAID 0. What happens here is I now have two bricks defined. I've said that these two bricks are part of a stripe. So now when a file is written, the individual file is actually broken up into chunks and written, as evenly as possible across the multiple bricks. What you end up seeing on the file system level is it appears on each server. If you were to look at the local file system, the local brick, you would see what appears to be the whole file, but if you analyze the actual contents of those files, you would see that a file on one brick contains part of the data, and a file on the next brick contains another part of the data, of course, depending on how many stripes you have. So we can take that striped volume and do what we did with the replicated volume and stack distribution on top of it. So once again, I've given it 4 bricks, and I said I want a stripe of 2. So what it's done here is it says, okay, well, you've given me 4 bricks and told me to use 2 of them, so I'm just going to do that twice and then distribute between them. So you see in this scenario that I have a striped volume between 2 bricks and a striped volume between another 2 bricks, and a file is being written. The first file is being written to the first stripe volume, and when the second file is written, the distribution protocol tells it to write to the other set of stripe volumes. This is the graphic that has a little bit of an issue here, though. You're striping in this case to multiple bricks on the same server. We'll get into graphic here in a little while. There's a good learning example because one of these graphics was actually written kind of funny. So we'll look at a striped replicated volume. So again, layering up the functionality here. We're not doing any distribution. In this case, we're striping and replicating. So we have multiple striped volumes, and every time a file is written, it is being written to, it's being replicated but striped twice. So we have a set of stripes over here, a set of stripes here, and every time a file is written, it's written to both sets of stripes. So we've essentially told Gluster, here are your 4 bricks. Now do 2 stripes and 2 replicas, and because of that, it's not doing any distribution. There's nothing left over to distribute to. So now we can get into the pretty complicated scenario of stacking all of these pieces up, and we now have a distributed, striped, replicated volume. Now the capability of doing this is actually only as of GlusterFS 3.3. If you go back to 3.2, it will not allow you to create this 3 layers of functionality here. But you can see what's going on here is now you have 2 striped volumes with 2 replicated volumes in each of them. So when a file is written, it's getting both striped and replicated. And when the next file is written, the distribution piece of it is coming into play, and it's writing it to another set of striped and replicated environment. That's the graphic we're going to come back to in a little bit. First, we'll take a little bit more of a look at data access. So we talked about the Gluster native client. So Fuse is the kernel module that's going to let you access a file system, allow a file system to be created in user space. This is the big advantage here is that we're not having to actually get into the kernel code, and we get to stay safely outside of that and still get all the file system functionality that we need. When you use the native client to mount to a GlusterFS share, to a volume, you're going to be able to specify any of the nodes. So I'm going to be able to say, okay, I want to access this volume, and I can say I want to access it on that particular node in the cluster. And when that communication gets started, the client is actually going to say, okay, now I know where all of this data is, and it's going to be communicating directly with the individual nodes that are storing the data, rather than always going through the node that you mounted to. That's one of the advantages of the native client. So, okay, so that's the part there where it says the native client fetches the vol file from the mount server and communicates directly with all nodes. So this is recommended for the high concurrency environments where you need the good write performance. So NFS, as I mentioned before, this is built in. Go ahead.
For native Gluster client access, do we have or are we getting any locality information for replicated volumes on reads? As far as I know, right now, when we're reading off the replicated volume, it's essentially arbitrary whether we're getting data that we have on local break. It's actually, I'm sorry, this would apply to distributed replicated or striped replicated volumes. We have data on the local break. It's actually kind of arbitrary or random whether we're actually reading off of that or from the other, from another node.
Right. Whether.
I think we currently don't have any of that locality information in there that we could, that client could use. Is that changing?
Jeff, can.
It has changed from. In Trump, okay. So it's coming in 3.4.
Yeah, also the default behavior is the first lookup for whichever node responds. Also, it picks basically that node. So if your local node is faster than your node chances are.
Oh, okay. So if the local node is actually busy doing I/O,
Then
it will be
it
smart enough to. Okay, that's cool.
That's the default behavior.
Right, so it's based on whichever one responds first, right? So which is most likely going to be the local node.
And it's perfect.
Right. Okay. One thing that I've discovered in my own testing of this, and I think we pointed out when I brought this up once before, that this is actually a bit of a bug. Rick, do you remember, not interrupting you there, but we brought up the fact that with the client you actually have to specify to mount with version equals 3 because of the error that it basically comes back with a right. And for some reason that wasn't happening. I remember having the discussion before. Mm-hmm. Yeah. So I wanted to point this out because if you do get home and you start messing around with this in your own environment, you go to mount it up, you may find that when you run the NFS mount command, you're going to be treated with an error in response. So just keep in mind that you actually need to inform it to mount with version equals 3. Standard auto mounter is supported. You can, again, like the native client, you can make the mount to any node. But with the NFS client, that once you make the mount to a particular node, your communication, all of your communication to the bricks is going to be filtered through that one node. So this is one of the detriments of using the NFS protocol instead of using the Fuse native client. But on the other side, you can get better performance for lots of small files because of the NFS caching that's built in. So again, accessing your data with CIFS, as I described before, this is going to be a little bit more of a manual configuration that you have to do outside of Gluster. You're going to use the Fuse protocol to mount locally and then reshare out with a Samba configuration of your own choice. Okay, so I'm not doing a live demo here, but what I have in this next set of slides is some screenshots that are going to show you what the Gluster command line looks like to do a lot of these things that we've talked about. So the first thing we're going to do here is prepare a brick. This is pretty straightforward. I'm putting this in here just so that we have it, a complete set of examples of what we're going to be doing from beginning to end. So all we've done here is we've created a logical volume and a file system on it. In this case, I do highlight and point out that we set the inode size to 512. This is important so there's enough room for the metadata information to be stored. Otherwise, additional blocks are going to have to be used to store that information. We've created a directory, we've mounted that directory up, and we've set it up in fstab so it's always going to mount. That's all there is to a brick. Okay, we just created a file system. But now that we've added that file system, let's start building our Gluster environment. So the first thing we're going to do is probe the peers. So from the Gluster command line, we see peer probe, and I've given it a host name, and that just is a resolvable host name on this machine. And then you can see peer status. Now, one thing that's kind of interesting when you look at this peer status command is it does not show the local machine that you're running the command on. So this output, in this case, is showing server 2 and server 3. We can assume through inference that I'm actually running this command on server 1, which is also part of the Gluster cluster in this case. It's not going to show up in the peer status command, but that's okay. So
After I heard you from last time.
yeah. So I always thought that was a little bit of a problem because it is certainly a bit confusing. It is good to know that in the future release, is it 3.4, I guess we're gonna see that, or? Okay, good. So anyway, if you have a later release, you're probably going to see this isn't the case. It'll actually show all of the hosts, including the local machine. So doing the basic thing that Gluster does, let's create a distributed volume here. You'll see that this is as simple as I'm going to create a volume. I give it a name. So I run the volume create command, the name next, which is arbitrary, and then I'm going to tell it what bricks to use. So in this case, I've given it server 2, brick 2, server 3, brick 3. And that server 2 is obviously the resolvable host name, and then :/, and everything after the colon is a actual file system hierarchy as it would look on the local machine. So in this case, I am using /brick2 on server 2 as a brick and /brick3 on server 3 as a brick. Because I didn't tell Gluster to do anything else, I've now created distributed volume. So when you see the volume info, the output on this shows I see the volume name, I see the type is distribute. It shows the number of bricks. Transport type is TCP, that's the default if you don't tell it anything else, and then it shows me the layout of the bricks. Brick 1, server 2, brick 2, brick 2, server 3, brick 3. Now this isn't fully ready to go yet. Gluster recognizes that you have those bricks, you've put it into a volume, but if you want to make use of them, you do need to run the volume start command. You see that there at the bottom of that example. So because this is so simple, we're going to jump from that simple scenario to let's put all of the layers in place. And we're going to come back to what we looked at before, which is that distributed, striped, replicated volume. So it was this graphic that we saw before when we put all of those layers together. This set of commands actually shows how to build that environment. So we've run volume create, we've given it a name, we tell it replica 2, stripe 2, and so we've told it 2 stripes and 2 replicas, but we've now given it 8 bricks to use. So with essentially the leftover set of bricks, because we told it 2 and 2, that's only 4, but we've given it 8, it's going to do the same thing with the other 4. It's going to distribute between 2 configurations that look exactly the same. Now, you'll notice when I pass this command, that green highlighted bit is complaining to me, and that's because whoever created this graphic didn't take into account that this was not an optimal scenario. What we're doing in this case is we're actually replicating between bricks on the same node. And that has to do with the order that we've passed the bricks in it. It's going to set up the replication based on the order of that. So you'll notice when I passed the 2 bricks from server 1, I've got export 1 and export 2 from server 1 listed first. So when it sets up the replication, the first thing it does is it replicates between the first 2 bricks. Because the first 2 bricks are on the same node, Gluster is actually warning me in this case, this is not optimal, why would you want to do this? But it'll let me go ahead and continue. And then I can build out the environment. So just taking a look at the pieces of the command that set this up. So you can see that the test volume name that I gave it when I passed the command is the distributed volume, which is the top level of the logic that we're looking at. The next piece was the replica 2. So you can, if you look at the graphic, you can see by the way the graphic is laid out that it's replicating between nodes on the same, between bricks on the same node. And then it is striping between the replicas on the 2 different nodes. And then finally, the distributed volume, it's doing this essentially twice. So let's take a look at how we fix this. And this is just as simple as rearranging the order of the bricks. So we run the same command this time, but you'll notice this time, and I've highlighted this for clarity, that I've given the bricks in pairs of bricks on different servers. So the first 2 bricks are on 2 different servers. The second set are on 2 different servers. And so I actually end up now with an environment where all of my replications are across bricks that are on different servers, which is a much more optimal scenario. You'll notice now if I run the volume info command on the test volume, I get all of the information that I need to see. I get the volume name, test volume. You'll see that it shows distributed, striped, replicated, because I've given it all of 2 replicas, 2 stripes, and 8 total bricks. Shows that it's created, not started. You can see it does a little bit of math logic for you there, just for your reference. 2 by 2 by 2 equals the 8 bricks that we have. Transport type is TCP, which I actually did explicitly imply in this one, just so you can see that in the command up there. And now it shows the brick layout, and you'll notice that the order of the brick layout is the same order that I put them in the command, and the replication is in those pairs. So we have an existing volume, and we want to play around with the bricks that are in there. So in this case, simple scenario, let's add a brick to it. So volume add brick. You see all these commands are very straightforward. Volume add brick to this volume, and then I'm going to give it a new brick to add to it. Now, when I do that, it's not going to be, well, you'll see in some of these later commands here. I'll show you. The next set is showing removing a brick. So in this case, I do a volume remove brick, tell it the volume, and what brick I want to remove. Now, you'll notice at the end of this one, I have to say start, because when I'm removing a brick, I obviously inherently need to move data around to free up the space on that brick. So I tell it to start, and then I can run a status command, and that status is going to give me some of that output that you see there. So in this case, I can see that it shows that it's moving that data. It shows it is in progress. Now, once that status comes back and says complete, I can run the commit command, which is going to officially remove that brick from that volume and free it up for whatever you need to do with it. So in the last little set down there, we see the volume rebalance command. So when I've added a brick to a volume, I now need to essentially reshape that volume so that that brick is available for use. There are a couple of different things I can do here, and the first one that I'm showing there is I'm running volume rebalance with the volume name, and then I'm giving it the fixed layout, and then telling it to start that process. Now, in this case, all it's doing is changing the architecture of the bricks in that volume and making that new brick available for writing data to. It is not moving any existing data around. So even though that's part of the rebalance command, it's not actually rebalancing any existing data. So when I start that, when that process completes, what you've essentially got now is a new space for files to be written to, and because that space is free and available, the elastic hash algorithm is now going to use that space for new files that are being written. If I run the rebalance command without fixed layout, we're actually going to be doing, in this case, a full-blown rebalance. This is a pretty heavy process, and you want to be careful with the scenarios that you might actually use this in. If you have lots and lots and lots of data, this is going to require some heavy lifting by the system. Yes?
Could you explain a little more why that is such a heavy lift operation? I mean, others, like for example, Swift has a partition grading, and it knows when you add new windows, it knows pretty exactly what partition it has to move. It doesn't have to recalculate the whole ring. Set has placement groups where it does, which basically apply the same process. Why is this such a heavy lift operation?
So in this case, by giving it a new brick and telling it to do a full-blown rebalance, the hash algorithm is now going to be run against every existing file that's on the system, and it's going to make a new decision about where those files need to go to redistribute those files as if that brick had been there in the first place. So you're going to end up with a lot of disk activity and network activity inherently just by moving that data onto the new bricks.
That's a relatively well understood problem, and there's algorithms to deal with that. And I wonder, are those not being used?
If you have, say, 8 nodes and now you are adding 9, 10, 10 more, if you have to level based on equal capacity, you still have to move the data. Any data movement is expensive. The fixed layout is cheap because it only fixes the hashing. Hashing is internally every directory thinks it has its own hash namespace. So fixing the layout is pretty simple operation.
Okay, so like straightforward question: if I extend my gross available storage space by 10%, will about 10% of the data be moved, or significantly more? Because that's the problem that you're trying to solve.
Yeah, so the first part is first, you have to move 10% data.
You have to move something. Yeah, no, that's fine. That's fine.
Yeah, the 3.2, until 3.2, rebalance was not an easy. Yeah, it really moved a lot of data, more, not 10%, it probably moved like 70, 80% of the data.
Well, that's the
Yeah.
classic. Like if you're not using like a hash string but just a modulus, that you get the same problem.
It was just basically a crude rebalance
Yeah.
implemented there.
Yeah.
The elastic hashing algorithm itself allowed you to move very efficiently, even specifically in a particular folder, you can take a group of files and level them. But the rebalance implementation was very poor.
Okay.
So that was fixed in 3.3. 3.3 now, what it does is, it's still not so granular that exactly which file you have to move, but it's good enough. It's significantly better.
Yeah.
What it does now is it basically picks one folder and then it fixes the layout. So every node has already some files and it already matches the new layout. So only the delta is moved out.
Okay.
The ultimate approach, if we exactly implement the original specification, you can even pick a very tiny set of files matching one particular bit, the virtual bit on a particular folder and move them. But what we have now is pretty easy.
Well, exactly 10% will move, but close to close. Well, if it's not 90, that's good.
So we'll look here at migrating data or replacing bricks. So in this case, instead of just adding a new brick or taking a brick out, let's say for whatever reason I want to replace a brick that's already existing. Again, the command is straightforward: volume replace brick, which volume, which brick I want to replace, and what the new brick is, and start. Now this is essentially doing the process of removing and adding a brick all in one simple swift move. Again, I have to start it. I can't just run the command like I can when I add a brick initially. I have to start the solve. Data is going to be moved around. When the data is finished, you're going to get a migration complete message when you run the status. And then once the status shows migration complete, you can run that commit command, and then the old brick can be removed from service. So there are a lot of commands that you can use to sort of get into the deeper level of system administration of Gluster. I've thrown a few up here that are going to be just more common examples of stuff you might run into. This is stuff I certainly recommend you dig into when you set up a test environment and see what options are available, check the documentation. But I just wanted you to see sort of the format of some of these commands. If you want to set authorization for how data on your Gluster volumes is accessed, then we have the volumes. The volume set command is sort of the core command for applying these other attributes. So I'm saying volume set, the name of the volume, and I'm saying auth allow, and you can see that I can pass like an IP address wildcard there, or and the same thing, auth reject, don't allow anything from the 10.anything IP address. Pretty straightforward stuff. There are NFS specific commands that are in there as well. Keep in mind that with the built-in NFS server, I'm not doing something like editing an Etsy exports file. That's not there for me to do. Gluster's managing that for me. So a lot of the stuff you might want to do as far as NFS specific configuration is also available in the volume set command. So you'll see here we did a volume set on that volume. If I want to set my NFS access to read-only, I can do that here. Or if I want to disable NFS altogether because maybe I'm only going to be using the Fuse native client or or that in combination with Samba, I don't want to use NFS, I can turn that off entirely here. You can also dig into a lot of other options that are in there, like I said. I've got a couple of examples there of the set read-only for everything. So in the previous command, I show setting read-only for only the NFS protocol, but if I want to set an entire volume as read-only, I can do that here. There are also a lot of performance tweaks that you can do. In this case, I show doubling the cache size here. So I've given it a value that's double the default. So digging into the performance of your volumes, there are a couple of tools that you can use to get some insight. The first one is a volume top command. This gives you a lot of cool output here. There are a lot of different options you can pass to this command as well to get different kinds of detail. In this case, I'm just showing an example where I said, give me the volume top of this volume, and I want to see the read values on a brick level of this brick. And the last little option that I passed there is list count 3. So show me the top 3. Show me the top 3 read activity based on the brick volume, based on the brick on this brick. And so you can see it's going to show me the read count of some individual files that are on there. So when you run this volume top command, you can see there that I showed read and brick. You can run that as read against directories or against files or write against those. There's a lot of extra options you can dig into there. There's also an interesting little performance tool that you can run there that are part of the top command as well, but you need to be careful with these performance analysis tools because they actually do a DD process in the background, so these can impact your system performance when you run them, but very good for benchmarking performance. So if you want to get, the volume top command is good to give you a point in time information, but if you want to get some trending information, you can collect that with the volume profile tool. So volume profile the volume and I tell it to start. It's really all there is to it to get it started, and now it's starting to collect data, and it's going to continue to collect data until I tell it stop. At any given time while it's running, I'm going to run the volume profile on the volume until it pass the info command to it, and you see a truncated example of the kind of output that you get on this one. What it's going to show me is read and write information at different block sizes. The ellipsis that I put in there is cutting out the other lines of output that just wouldn't fit neatly on the screen, but you can see there that the columns that it shows are 1 bit plus 32, 64, so you see those block ranges. If this continued down, you would see higher and higher block ranges and more information on those. You also get the latency output there at the bottom, and then finally it shows you the duration that it's been running and the total bytes read and written during that duration. Yeah, I imagine there's going to be some performance hit with running that, but I don't think it's excessive to run the profiling tool, is it? It's
technically it should be acceptable to run all the time.
Right.
But
It's essentially logging.
It's basically a very lightweight translator collecting information. So ideally we wanted to keep it running all the time, but early in the development I noticed that QA was reporting some overhead that was not acceptable, but that was more like a bug. I don't know the third state.
Okay. So realistically, it should be very lightweight. You should be able to run that and collect information on a production system without impact. Again, it is logging information, so obviously it's storing that data somewhere. I'm not quite sure what it does in the background as far as managing, the storage of that data and rotating it. But it is run per volume when you run that command.
Translator you saw in the map, basically it's loaded on every server, every grip, and then every client too. So it keeps track of every node in the cluster, what's happening. And then the profile information is that every call that happens in the call stack, it basically measures latency. And that data is kept where though? I think it is in memory, but I don't know if it's ready
So a quick look at the commands involved in setting up georeplication, just so we have a little understanding of that. Again, you see the very simple, straightforward commands, volume georeplication, I tell it what volume, and then I'm passing it what host I'm going to replicate to. Now you'll notice in this case, I show a couple of examples here, just so you see the differences in the way you can pass this command. In this case, I've given a remote host name, and I've given it a colon and a volume name. Now this basically tells Gluster to interpret this as the remote machine is also running a Gluster system, and that is a remote volume name. I tell it to start, and then it gives me the information that it's successfully started. And when I run the status on that, you can see shows the master. The master is the name of the volume that I told it to replicate, and then you see the slave, and it shows gives that little Gluster protocol tag on there to show you that this is replicating to a remote Gluster volume. Shows the name and the volume, and gives me a status of OK. You can, if your scenario calls for it, you can perform a georeplication to simply a remote SSH share instead of a remote Gluster volume. I still have trouble understanding why you would do this, but I imagine there's a scenario where you would. But just to kind of show how that would be set up, you do actually need to set up SSH keys for Gluster. Those secret.pim has got to be in place. And then you see in this case, I've actually passed it a username at the remote host, and when I give the directory structure, I've now given it a :/, which is indicating that it's actually a directory structure and not a volume name. So it interprets that shorthand appropriately, and you can also see in the output of the status command, it shows master volume, and it shows the slave as actually being a remote SSH share. So I can send this directly to a remote file system. Granted, if you're using Gluster to store loads and loads of data and then replicating to a remote SSH file system, what is backing up the data on your remote, what's your backend storage in that case? That's why the scenario seems kind of strange, but it's there. In this case, I show another instance of running the volume info. I've truncated the output that we've seen before just to show you that at the end of that, once I've set up georeplication, the volume info command actually shows the options that are reconfigured. It says georeplication is on. So that little bit of output is put in there. So we'll close this out with just a little bit of information on some use cases. Common solutions, we've talked a little bit about these. Media content distribution, backup, archive, disaster recovery, large-scale file servers. These are all pretty straightforward use cases where Gluster really excels. Where I have lots of data that's being accessed by lots of clients that I need to be able to scale out at a linear pace inexpensively. This is really going to be the best use scenarios. Another one of the interesting ones is HPC. I like that scenario because it's a little different than some of the other use cases. The Gluster backend storage being able to scale in a similar way to how you're going to scale your HPC environment. You're going to be able to use that commodity hardware in a similar fashion. So it never made any sense to me that if I have an HPC system that's outputting tons and tons of data, and I've built this HPC system with this wonderful, inexpensive commodity hardware and commodity software systems, now all this large amounts of data that it's dumping, I either have to put it on some skimpy system that's hard to access and is limited in capacity, or I have to put it on this really expensive back-end SAN. So I think this is a really cool place for Gluster to excel as well. So you can scale along with the HPC system. And then I think another one of the things we're going to see more of in the future is in infrastructure as a service environments, using Gluster as a storage backend for that. We also talked a bit before about Hadoop. I think John Mark actually covered this fairly well. It's certainly an interesting scenario to be able to use something that is a POSIX compliant file system as your storage backend for Hadoop without having to really do anything significant to Hadoop to get it to do that. You essentially get a seamless replacement for HDFS, but you get the added benefit of being able to access your data as files rather than having to transfer it into the HDFS system via your manual processes you normally would need. So these are a few customer scenarios just to kind of show where Gluster has been used in real life, and a couple of these are pretty high profile and obvious. CIC electronic signatures, these guys are doing a lot of processing of electronic signatures, as their name indicates. They need to be able to do this stuff fast, and they need to be able to scale quickly, and they need to be able to do it in the cloud. And what they were running into was the performance of the storage environment and scalability of storage environment while they were in the cloud was really limited, and their SLAs are demanding. And what they're able to do with Gluster in Amazon Web Services is set their standard for those SLAs, and they were able to move far beyond those. They were actually able to get performance metrics that are well beyond what they were even shooting for. They were also able to accelerate their cloud migration. Once they put Gluster into the plan, their move to the cloud was able to go a lot more quickly and smoothly. This is the big one that's always fun to tout because most of you guys are probably running this on your device of some sort. Very well-known environment. So you can imagine a lot of this music that you're streaming from Pandora is being hosted with a GlusterFS backend, which I think shows a really significant use case for Gluster that we all can relate to. The amount of storage, I think this data is probably out of date at this point, but 1.2 petabytes of audio served per week, 13 million files. I think we show that I thought this one had a number on it for how much data they were using. So what we talked a little before about scenarios where you may or may not use the rebalance, and hot content is one of those places where rebalance is probably not something that you want to do. So as Pandora needs to expand out their storage infrastructure, they can add additional Gluster nodes, additional bricks of storage, and by not rebalancing, they now have the newer technology, the more modern, the faster stuff that is free and available. So the hashing algorithm, the elastic hash algorithm, is now going to be able to take advantage of that for the new hotter music files that are coming in and being accessed. So you want that to sit there, and you really kind of want your older stuff that's being accessed less and less and less to sort of stay on that older, slower stuff that you can migrate off at some point later. Yes?
Is there a way to have Gluster routes, particularly for something like Pandora, where obviously the replication is limited to geographic replication, but how could they pick up the benefit of geographic storage more of a CDN type of, where if they're storing using geographic replication, and they also get the benefit of being essentially closer to their rather than having to go back through whatever domain the person initially contacted.
So using the Pandora's backend storage in conjunction with the content distribution?
Well, using it as
Right.
I mean, they gave a talk at Red Hat Summit, what they did, so they're using it very flat. They're just using web services on the same storage service serving stuff. They're not using Gluster access for the whole client. So there's something between some software between these. So they did.
Today they are using they have a caching layer too, but the PR4 version, the next upcoming version of Gluster, we will have active geographic replication. Then we can look at those metrics. That is not good.
Basically make that decision which one's closer to people there.
Yeah.
Pretty much they're, again, they're theoretically open what they did in public, but they were just basically following down all the data and be only replication is trivial. Easy to have to take it. Yeah, all they did is basically was storing the gold individual on the file and living
Today you can read from the remote copy. The writes are not allowed. Next release we are planning to do all active multi-site.
Right. So yeah, part of the answer there is obviously that we're limited with the capabilities of the current release of Gluster, but with the future GlusterFS releases and two-way replication, that's going to increase those capabilities for sure. So Brightcove is another interesting scenario. They're doing something pretty similar to what you see with Gluster, but with files that are significantly larger and a pace of growth that's very significant. So these guys are storing videos instead of music, and as times are changing and they're needing to store and distribute different types of data, the videos, as you can imagine, as you're getting into HD formats, the amount of storage that they're able to, the storage that they need to use and the information that's being streamed is increasing significantly. So we show here a petabyte of total capacity. Again, this is probably outdated. Their project was to grow this pretty significantly. But similar to Pandora, they're able to use this to scale very quickly, inexpensively, and be able to administer in the long run with a small set of administrators. I think it even says one administrator to manage day-to-day operations, which is pretty significant for a storage system that's holding even a petabyte of data. Higher reliability, path to a multi-site at some point in the future. Again, probably taking advantage of the future replication stuff that we're going to have. And then getting to that HPC scenario that we talked about. This Pattern Energy is a company that's actually using this. They had an interesting scenario where they need to track weather patterns, and they do this for a couple of different reasons in their business. And they have an HPC system that they needed to build out to do that. And again, generating lots of data and scaling pretty rapidly. How do I take that data and put it on a back end that scales with my HPC system? So they were able to utilize Gluster for that function and get a lot of benefit out of that, and a lot of benefit to their business for this the solar and wind patterns. Helps them identify not only patterns for energy consumption so that they can route energy in the ways that are going to be most efficient, but also for things like deciding where to put a wind farm at some point in the future. If I can understand the wind patterns, I might have a better idea of where my windmills are going to be the most efficient to be placed. So a lot of good information coming out of that. And that's all I've got for you guys today. Just say thank you to everybody. I've got some resources up here. Again, I put up that the URL to the survey for some feedback. I appreciate everybody providing that feedback. And I've got my contact information up there, as well as some links that are useful, and catch us on the social sites as well. Any questions?
We have a couple minutes for questions while that goes being set up.
Is there any limitation to the brick size? So if I decide to create a cluster with certain brick size, can I add different size of bricks later on? Or do they need to match?
That's so. From a performance standpoint, there's an aspect to the size, right, as well. I'm not sure how to best answer the question. There's nothing in Gluster that's limiting the size of the individual bricks, right? So I can put different brick sizes into the environment, but they're of course going to be up to the individual scenario that you need. Right. Right. It takes all that into account. Yeah, I think it's a little related too to the question that came up earlier about when you have a replicated volume, how does the client know which of the replications to access? And AB had explained that it's basically whichever one is responding first. So we have that ability to, for the client, because the client is aware of the multiple locations for the data, it's going to essentially ask for all of it, and wherever it gets the response back first, it's going to communicate with.